4 applications of differentiation. First, we're going to do our visual aid, and we have this image of a man running away from a rock. So you see the rock falls down at a steady rate, the man runs away at a steady rate, and the question that'll be posed is at what rate does the distance between the man and the rock change? And as you think about it, we're not going to solve right now, but keep in mind it has to do with this right triangle we can make between the point where their paths cross, and then the distance from the rock to the ground and the distance from that point to the man. This creates a right triangle, and this hypotenuse, the distance away, is going to change over time, and that's what we can solve for when we go to solve these kind of problems. But first we're going to talk about straight line motion, and you might have seen something similar in maybe a physics class, but in here when we're talking about calculus, if you're given a point function, you take the derivative, or a position function, excuse me, you take the derivative and you get the velocity function, and if you get a velocity function, you can take the derivative and get an acceleration function. So in this case, a point moves along a line according to the function f of x equals 3x squared plus 5. X represents time in seconds, and f of x represents distance away from a point in meters. So we're going to find the speed of the point at time x equals 10. So if we're told to find speed, first we need to find the speed function. If we're only given the position function, so we'll write down 3x squared plus 5 x squared plus 5. This is our position function. Going to have to take the derivative if we want to find the speed. So the derivative of 3x squared is 6x. And the derivative of 5 is just 0. So we have 6x is our speed function, and we want to find it at time x equals 10. So we'll just plug that in. 6 times 10 equals 60. And then meters per second, because we're given meters. And seconds are our 2 units. Pretty straightforward, pretty easy differentiation here. And now the more complicated unit we're going to talk about is related rates. So it's real world context of what you've learned hopefully in Unit 3. Those related rates problems should make more sense of the equations. However, they lead to some complicated problems. We'll keep it on the simple side. This is a common problem where a ladder is sliding away from a wall at a constant rate. Ladder leaning against the wall is falling down with the base sliding away from the wall and the top moving down at a rate of 2 meters per second. If the ladder is 13 meters long, find the rate at which the bottom of the ladder moves away from the wall when the top is touching the wall 12 meters above the ground. Now this is a lot to read, so we're going to do it step by step. So first we're just going to draw a picture of the problem. So we have a wall. I'm going to assume it's a house, so I'll draw a little house. Just so we know what we're looking at, our ladder is sliding down along the ground. Let's draw the ground. This is our ladder, this line here. And now we have this right triangle here, so we're going to label our 3 sides. This is A. Starting here, this is A. This line right here is our B. And then the hypotenuse C is just the length of the ladder. It's right here. And that's the first step. There's 3 steps. Identify variables, create a function that relates the 3 variables, and then solve for the variable. So we have our first step done already. We're going to write down our variables here just to keep track. A, B, C, and these are going to be the lengths. Now we'll make a function that relates them. We already know if we have a right triangle, the function that relates A, B, and C is going to be A squared plus B squared equals C squared. Should be a familiar function, the Pythagorean theorem. Squared. And now the part that calculus comes in, we're trying to find the rate at which the bottom of the ladder is moving away from the wall. Anytime you hear rate, you should be thinking derivative. We're given one of these rates. So anytime we're given rates, we're going to take a derivative. So we'll take a derivative of this whole equation. And we're taking it with respect to time, because the one rate we've been given is that the top of the ladder is moving down at a rate of 2 meters per second. So that tells me I'm going to rate a derivative with respect to time. I'm going to call time t. T is going to be my derivative. So the derivative of a squared is 2a, and then this related rates variable dA dt plus 2b times dB dt equals, same thing over here, 2c dt. And just to keep track, I'm going to add those three variables, dA, I'll just call them dA, dB, and dC, B, and dC. And we can substitute in what we're already told. So we've been told that the ladder is 13 meters long. That means C is 13. And we are finding it at the point when the top is touching the wall 12 meters above the ground. So that's 12 for our A value. Then the remaining value, we have a Pythagorean triple. If you know, it's 5, 12, 13 is a Pythagorean triple. You could have plugged it in if you didn't already know, and in some cases it'll be an equation you don't already know. You could have plugged it in with 12 squared and 13 squared and then solved for B. In this case, 5, 12, 13 is a Pythagorean triple, so we can just assume that B, or we just know that B is 5. And then we're also given some rates. So the top of the ladder is moving down at a rate of 2 meters per second. So that's going to tell me this dA dt, the rate that dA changes over time. So that is going to be, we're going to say -2, because A is shrinking as the ladder falls down, the top goes down, the bottom goes this way. That's just shrinking, so our dA dt is going to be -2. And then we can also say what dC is, because the length of the ladder isn't changing, and that's part of the problem. The ladder wouldn't ever grow or shrink as it falls down, so we'll say that dC is 0. Over time, the value of C, the length of the ladder, doesn't change at all. So we can plug some of these in. So we have 2 times our A is 12. And our dA dt is -2. Doing the step of just plugging everything in right now. 2, our B is 5. And this is what we're looking for, is dB. It says find the rate at which the bottom of the ladder moves away from the wall, which is going to be our dB dt. And that's what we're looking for right now. This is the answer to our problem, is dB dt. Now last thing, we'll put this back in here, over dt. So this is the variable we're trying to solve for, equals 2. Our C is 13, and our dC dt is 0, which means this whole term is 0. Can do the math. This is -48 plus 10 times dB dt equals, this whole term I said is 0. Add 48 to both sides. Now we're just doing algebra. 10 dB over dt equals 48 Final answer, dB dt equals 4.8. Now in context, that means that the ladder is moving 4.8, our unit is meters per second, it's moving 4.8 meters per second away from the base of the house at the time when the ladder is 12 feet high. That's our answer there. And we know it's true because we can we can assume that B is growing. If you can just picture it, the ladder is moving down here, it has to be moving out, and we have a positive number. So that checks out, and we also already know that the ladder isn't shooting off at a million miles per hour. So our answer of 4.8 makes sense. If we had a negative number, if we had like 1,000, we would maybe question the answer, but we can assume that's right. Last thing we'll talk about is L'Hopital's rule. And it's just anytime you have an indeterminate form when you're taking a limit, you can rearrange the function into a fraction, and then you can take the derivative of the top and the derivative of the bottom, reevaluate the limit. Sometimes you can get the answer to an indeterminate form. We'll do some examples, make it easier. So first one is x to the 5th over 2 to the x. X to the 5th over 2 to the x. Now when we put in infinity, the way we check in this kind of problem is we'll just substitute in infinity for x for both of these, because we're taking the limit as x approaches infinity in this problem. So infinity to the 5th is infinity, and 2 to the infinity is also infinity. So we get infinity over infinity, which is on our list of indeterminate forms. It's the first one right here. So what L'Hopital's rule is, we can take the derivative of the top and the bottom. 5x to the 4th will be the derivative of our top over 2 to the x times natural log of 2. And you may not know logarithmic derivatives yet, but that's the derivative of anything that's a constant to the power of x. You do the function times natural log of the base number. Now we can substitute infinity back in. Unfortunately, we're still going to get 5 times infinity to the 4th is infinity, and 2 to the infinity times a constant is still infinity. So we still get infinity over infinity, but fortunately we can do the same thing again, take the derivative of the top and the bottom. We will get 20x to the 3rd over 2 to the x. And we'll treat this natural log of 2 like a constant that we're being multiplied by, so it won't affect our derivative. So it'll be times natural log of 2, and then times natural log of 2 again, because the derivative is going to have us multiply and not the natural log of 2 in front. So we'll just say natural log of 2 squared, if that makes sense. 2 to the x times natural log of 2 times another natural log of 2. We're simplifying that. Probably notice already that if you substitute in another infinity, we still get infinity on the top and infinity on the bottom. However, this power is getting smaller. Every derivative we started off with x to the 5th. Now we have x to the 3rd, and this number is only getting bigger. We have 2 to the x, and then just a bigger constant that we're multiplying by. So if we keep going, the next derivative is 60x squared over 2 to the x. 2 to the x times natural log of 2 now to the 3rd power. Then our next one is going to be 120. We're going to speed it up a little bit. this results in the same infinity over infinity. 120x over 2 to the x times natural log of 2 now to the 4th power. And this still results once again in infinity over infinity. So we're going to go back up to the top. And now one last time, the derivative of 120x is 120 over 2 to the x natural log of 2 to the 5th. And now if we substitute in infinity on both sides, we get 120 over this bottom evaluates to infinity. 120 divided by infinity approaches the value of 0. So we can find 0 as the answer for the first one. Second one is a little bit quicker. We have the sine of x over x as it approaches to 0. Alright, sine of x over x as it approaches to 0. Sine of x divided by x. If we substitute in 0 for both of these, we get sine of 0 over 0. Sine of 0 is 0. Sine, or just x, if we substitute in 0, is 0. Sorry. 0 over 0 is the second of our indeterminate forms right here. So we will take the derivative of both sides. We get cosine of x over 1. Now we can substitute in 0 for both again. Cosine of 0 is 1 and divided by 1. So we can get 1 as our answer there. Last one, limit as x approaches infinity for x cubed over 10x squared plus 3x plus 3x plus 8, excuse me. Scroll back over. So we have x cubed over 10x squared plus 3x plus 8 is our big function here. If we were to substitute infinity in for all the x's, we will get infinity over 10 times infinity is infinity plus 3 times infinity is infinity plus 8. So we get infinity on the top and infinity on the bottom, and that is still falls under the infinity over infinity. So we need to take the derivative. We get 3x squared over 20x plus 3, and then the 8 evaluates to 0 when we take the derivative. So we still have, if we substitute in infinity for x, we still get 3 times infinity squared, that's infinity, over 20 times infinity plus 3, also infinity, so we get infinity over infinity again. We'll take the derivative one last time. 6x over 20 is 3. Take the derivative, it evaluates to 0. 6x over 20 is infinity divided by 20, which still evaluates to infinity. So we can say that this limit approaches infinity.